annotating the videos with. Not finished yet, but okay. So Jyotirmoy Lokayakam, I'm annotating the little videos with Jyotirmoy link. Description of the material covered in each lecture, so it will be more useful for people who want to look it up. Okay, so let's continue. So today we're going to, the first thing we're going to do, so you remember last time we proved this no-ghost theorem. The no-ghost theorem for the world sheet of the string. And the statement of that theorem was that that while if we look just at the first quantized string with the matter stuff and then BC ghosts, we had many states in that conformal field theory. Okay, and these states had negative norm, positive norm, zero norm. Okay. However, if we focus attention to the cohomology of the BRST operator, and we also focus attention on states that obey B naught on state equals 0, then there was a cut down from the states of 28 oscillators to the states of 24 oscillators. In particular, we showed that this cohomology was in one-to-one correspondence with the Hilbert space of the line code quantized string, and we also showed that the inner products on this cohomology, which are well defined, I remind you, because any state of 0 norm, any state that's Q exact has 0 inner product with every other state. We also showed that the inner products in this cohomology were in one-to-one correspondence with this line code quantization system. Okay, so I'm going to start today's lecture by just giving you two examples, giving you the example of how this works. Oh, and we ended last time's lecture by pointing out that in order, when we, in the argument for the cohomology, we actually found representative elements of every cohomology. We actually constructed a vector, a state that was in one-to-one correspondence with the states of the line code quantized string. And we noticed that state had no n minus B or C oscillators. In particular, it had no B or C oscillators exactly. Okay, so using that observation, we basically argued that there was a way of choosing elements in cohomology such that they were in the BC ground state and only the matter stuff was excited. Okay. Now, in this restricted class of states, we still have the analog of a cohomology problem. It's not quite a cohomology problem. It's something like that. Because this restricted class of states still has 26 oscillators. And we know the right number of oscillators is 24. Okay? Because all we've said so far. We're not, in my restriction, I'm not imposing n minus C. Just B and C oscillators. Okay, so we still have 26 oscillators. The right number is 24. So okay, this is sort of physical subsector of the whole thing, because this ghost stuff in the end is some jazz, some funny pop of gauge fixing business. It's the other part of conformity theory, it's physical. So it's nice that we can deal with representatives of cohomology that have nothing funny going on with the ghost, just everything interesting happening with the matter. But already, even here, we have some conditions. You remember that we showed that the states for Q exact, Q closed, imply that Ln on the side equals 0 for all n greater than equals 0. Where this L now is just the matter sector L, except for L0, which is L0 matter minus 1, where this minus 1 came from the normal ordering constant of L in the ghost sector. Okay, the fact that the ghost factoring at L0 equals minus 1. Okay, so we show that this had to be true. So that's one set of conditions. Roughly there's one condition for each oscillator level, so that cuts down one oscillator each. So that takes 26 to 25. What takes 25 to 24? Okay? And the point is that even in this set of states, there remain states that are Q exact. Now, these states are Q exact, but they're not Q of some state in this set. The Q of some state outside. Okay, so we can't consistently this set of states and analyze cohomology. However, what we can do is to use the property of Q exact states, which was that Q exact states were always null. Okay? And all states that are null by the no-close theorem and that are also closed are Q exact. Okay? And then we realized that any state that was of the form L minus n on psi was null. And in fact was orthogonal to every physical state. To each physical state. Okay? So these were the states that we identified these as the Q exact states. And so in this physical representative set of states, the analog of Q exact states are states that are descendants of some state. The Q closed condition is simply the condition that the states be primary. States that are both descendants and primaries are physical but not so. They're gauge states. Okay, so now I'm going to very quickly lead you through a little computation at the lowest first level of closed string theory to try to examine Q cohomology. We first do this in the physical sector and then also do it including the BC twists. So we'll first do it in this restricted set of states. Okay, so in this restricted set of states, now let us look at states at level 0. See, now in this restricted set of states, the only oscillators we need to care about are the matter oscillators. Okay, because we're saying that the course B and C system have a vacuum. Okay, so at level 0, what do we have? There's unique states. It's the vacuum, or more precisely, there's a unique state up to zero mode motion. The zero mode state. The state labeled by 25 momenta B. Okay, now the question, what is the condition that that is physical, that Ln annihilate the state for all n? Well, let's remember, Ln is a product of oscillators whose index numbers add up to n. But since if n is positive, not 0, that always means that there is at least one unpaired oscillator. For instance, L1 will go like alpha 1, alpha 0 plus alpha 2, alpha minus 1 plus blah. And this alpha 1 will annihilate the vacuum, alpha 2 will annihilate the vacuum, and so on. Okay? So it's automatic that this state is annihilated by all ln's by n positive. Okay? What about for L0? Well, for L0, we get the famous Marshall relation. Alpha prime p squared by 4 plus 1 or minus 1 is equal to 0. The minus 1, I remind you again, came from this. The zero mode, the energy of the course vacuum. Okay? Great. So this state is clearly physical. Now, question, can it be obtained by L minus n on some other state? The answer is no. Can somebody suggest now? What is the relation between the energy of L minus n on psi and the energy of psi?
N plus the energy of psi.
N plus the energy of psi, exactly. L minus n raises the eigenvalue of L naught by n units. Okay? So, if 0 was L minus n on psi, for any n, then psi must have energy n units lower than the energy of 0. But 0 is the lowest energy state in the theory. There's no oscillator state. There's no oscillator state which has, the lower energy than this. Okay, that's just clearly impossible. Okay? Fine. Now let's move on. So at at the zero sector, the lowest sector, we found that there is one state that's physical, and that it also is never cube exact. It can never be written as L minus N or something else. Okay, so this one state is a physical state. Fine. It's the classical constraint. Okay, of course we would have had the one state also like quantization, ground state and oscillator, so that's good. Now what? Now let's move on to the first excited state. Okay, so the first excited state, the various states are A mu alpha minus mu minus 1 on V. These are all the states at level 1. Yeah, I'm decoupling the left and right sectors. This is just left first. You can do the same. It's actually the same story with the right first.
This will be predicted over the
it could be times any right moving state.
Oh,
Okay, I'm just asking what condition we can say on the left moving part of the state. Then independently be conditions of the right moving part, and then there'll be level matching. Okay. The level matching actually will that will basically be automatic, because level matching is L0 is equal to L0 bar, but each of L0 and L0 bars will be set to minus 1. So the level matching part of it will be automatic. But let's get on to that. We'll get on to that. Okay, okay, good. So now let's look just at that. So we've got A mu alpha minus 1 mu on P. Okay. Now, first question: what constraint do we get from the fact that the state is physical? Firstly, there's a constraint from L0. But now the L0 constraint just tells us that alpha minus P squared by 4 is equal to 0. Because the minus 1 from this cancels the plus 1 from the fact that we're acting with oscillators will be 1. Okay, so we get the energy of that state is P squared, alpha prime P squared plus 4 plus 1 minus 1. So alpha prime P squared plus 4, so that's P0. Okay, now what about L2 and I? Well, L2 and I always have annihilation operators of at least oscillator number 2 or higher. As so L2 will give alpha 2, alpha 0 plus alpha 3, alpha minus 1 plus blah. Okay? And so this state will always annihilate the state automatically. That's not a problem. Okay? The only issue is L1. Now L1, the only dangerous term in L1 is the term which is the form alpha minus 1, alpha 1 mu alpha 0. It's the only term that is not automatically annihilated. Okay, so let's act L1 on the state, and what do we get? So the alpha 1 heats up the alpha minus 1 mu, and we get something proportional to alpha mu, and alpha 0 mu, but alpha 0 mu is eigenvalue proportional to P mu. So alpha mu P mu on P. So what we did, we said L1 on psi, that's right, yeah, L1 on psi is proportional to alpha mu. Okay? Where psi was equal to this. I wrote alpha this thing. Sorry. Clear? Okay. Now our physical state condition was that L1 on psi was equal to 0. So that implies that that A mu P mu equals 0. Right? Exactly. Now what is the interpretation of this condition? The interpretation of this condition is simply that every on-shell state of a photon or a graviton has transverse polarization. It's transverse polarization. Polarization that's transverse to the direction of momentum. Remember that in string theory we are only computing on-shell things. On-shell S matrix, and that's basically the interpretation of that. Okay, good. So we've understood the physical state condition. We've understood the physical state condition, the condition that L annihilates the state. But what about the condition that the state not be L exact? Okay, so if the state were to be Ln on some other state, tell me what Ln must be and what that other state must be. Suppose we had a state at level 1 that was L minus n on some other state. Okay, and what are the options? What could that state be and what must n do?
L minus 1 and
L minus 1 and what must the state be?
ground state.
Exactly. You see, because this state has energy 1, which is the second lowest energy in the theory. So the only way it can be L minus n on some other state is if it was L minus 1 L minus n on a state of lower energy. There's only one state with lower energy, which is the ground state. Okay? By the way, when I say energy, I mean the oscillator part of the energy, which is all that these L's get about. Right. The only thing it could be is L minus n of the ground state. Now, it has to have energy 1, the ground state has energy 0, the state has energy 1. The only thing it could be is L1, L minus 1 of the ground state. Okay? So let's work out what L minus 1 of the ground state is. So L minus 1, the only term that contributes, okay, it's a term with no annihilation operators on the ground state. So the only term like that is L alpha minus 1 mu times alpha 0. Okay? There's such a term acting on P mu. It gives you, it's proportional to P mu alpha minus 1. Okay? So such a state does exist. It's the state with A mu proportional to P mu. If A mu was proportional to P mu, then the state would be of the form L minus 1 and 0. Okay? Now, is a state with A mu proportional to P mu, is such a state a physical state? Well, let's see. The physical state must obey the condition A dot P is equal to 0. But A is proportional to P mu, so P dot P is equal to 0. But that's true from the Marshall condition. P dot P is equal to 0. Okay? So such a state is a physical state. However, it must be modeled out. It's 0 levels to be exact. What's the interpretation of such a state? This statement? Well, in Yang-Mills theory, you see, if we did this with the open string, which I've not yet discussed in class, what we'd be getting at the massless level is Yang-Mills theory, photons. We do it for the closed string, we get gravitons. Okay? But I'll make the statement for Yang-Mills theory because it's more familiar. Okay? The statement for Yang-Mills theory is simply that a shift in A mu proportional to P mu is generated by gauge transformation. Right? Because A mu goes to A mu plus del mu chi, it's a gauge transformation. So, if you take two different photon states, scatter them, and the gauge equivalent, they should give the same physical answer for the S matrix. Okay? So, that's what we're saying here. That gauge transformations of the external states, the difference between two states that is generated by gauge transformation is a state that is Q exact. Okay? And therefore, external states that differ only by gauge transformations are worldsheet states that differ only by Q exact terms, and therefore have the same scattering amplitudes. Okay? So, we see this working out very nicely, and exactly as we expected it, as it should work out physically. Okay? So, at the first level, we lose one polarization because of physical state condition, and we lose a second polarization because because states that are gauge equivalent are the same. Okay? You see how nicely space-time concepts that we're familiar with tie in with these world-sheet concepts that we just developed. Okay. Now, though we're not going to, you see, we have an abstract proof that this works to all of this. We're not going to bother to try to check it in higher and higher orders. Though it's worth your while to try to do so. I mean, it's worth. I'm not going to do it in class. It's worth your while to try to do so at level 2. You'll find that every level there are states that are killed by the physical state condition and states that are killed by the nullarity condition. Okay, and so. But roughly speaking, the fact that we have these extra null states at every level tells us, you see, each null state corresponds to a gauge invariance. So the fact that we have these extra null states at every level tells us that string theory has much larger gauge invariance than low energy field theory. The null states at the massless level are the gauge invariances we're familiar with in low energy field theory. String theory is much larger gauge invariance. It sounds like a very intriguing statement, and certainly correct in some sense, but it's never been put to any concrete, perhaps except for open string field theory where it's proved useful. And it's never, I mean, it's not been as useful a statement to us. It's not, this must be a deep statement in some way, but it's not been made concrete or either used to say something very interesting about string theory to my knowledge yet. There's probably something to learn here. Okay. There's some discussions. Okay, so this was just a general remark.
Is there any statement that if you want to have various participants, you should have so much?
Yeah.
You should have so much of it. Is there a statement which you can make it more precise?
Well, I don't think. Well, the answer is I don't know. There's probably been people who discussed this question. Okay, I'm not aware of the discussion. I'm not familiar with this discussion.
For example, can I just though it is not considered to do, can I just restrict to some spin and study that whether I can get something high speed?
Yes. Yeah, you could try that. Well, you see, you could do that at the non-interactive level. That would then be consistent because all these different states are physical; they don't talk to each other. But once you put interaction, you turn on interactions, nothing good will happen to that theory. So, I mean, I don't think there's some general statement that if you don't ask for good properties in the end, that you need null states at every level, that you need gauge invariance. But somehow, if you want the theory to be good in some sense, that you have to make precise. That's unitary, that's well defined, blah blah blah, all of that. Then this may be a requirement, but I shouldn't say much more. I don't know much. I mean, I'm sure there's been interesting discussion on this question. I'm not really aware of it, but I don't think anything terribly concrete has come out of it. Okay, good. Fine. So this is all I wanted to say about the implementation. So this is how the no-code procedure works, level by level in string theory. Okay, it's an interesting exercise to try to get you guys into at least one higher order, which I strongly recommend. But what we're going to do now is to try to now move on and see how we can do the same thing. How we can do the same thing. Just for for the full Hilbert space of the world-sheet theory, including the BLC first. Okay. So how are we going to do that? Well, so let's look at the full Hilbert space, including the BLC host. So what do we have to do? What we want to do is now suppose the states are Q closed and states are not Q exact. Okay? So, let's first start at level C. Now, let's remind ourselves what the current corresponding to this BRST operator was. Okay? The current corresponding to the BRST operator was C times D plus half straight. Plus BC del C. Okay, so let's already start. Let's already start at the lowest level. Okay, now you see that Q. Okay, Q could be written as Cn L minus N plus blah 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 contributions coming from the previous sector. Okay, but you see that if we count overall level, we count both matter as well as host level. Q has level 0. Right? There's a Cn, it's N minus. Okay? So, if you add Q on a state, it doesn't change the level of that state. So, this discussion of Q cohomology is in some sense even easier than the discussion of the L cohomology. Because if you're going to have a state that is Q exact at some level, it must be Q exact, it must be Q acting on a state of the same level. Because Q doesn't change the level of the state. Fine, so let's try to work this out. So now first let's work with level 0. Level 0 as before, there's only one state, it's mu. Okay? Level 0. That's none. Gautam, please feel. Yeah. Okay? Now let's add Q on the state. So what do we get? It's just 0 because either C is an annihilation operator or L is an annihilation operator. The only place where we have neither was C0, L0, but L0 on the state is 0. Okay? That part's a little glib. This part is L0 matter, but when you add to this part, you also get C0 times L0 host. Okay? And it's L0 matter minus 1, which is just 0. Okay? So when you work that carefully, this part, which is Q acting on P, is simply 0. Now that immediately tells us the answer to the cohomology at level 0. So what's the answer? We don't need to do a second calculation. What's the answer? Or I'll give you a second answer. So what's the answer? Somebody? This is a physical state. How do we know it's not Q exact?
Because Q of that is...
Yes. Make that precise. If it was Q of some other state, what would the level of that other state be?
So it should be the same.
The same. But we found that every state at level 0, there's only one, but okay, every state at level 0 is annihilated by Q. So there is no non-trivial state of the form Q of something at level 0. Okay? So we're through. This state is physical, it's also not pure H. Okay, so say we're through this. Okay? Now let's work at level 1. So level 1. Okay, so what can the states be? So they can be A times C minus 1 plus B times, alpha times C minus 1 plus beta times B minus 1 plus A mu alpha mu minus 1 on B. This is the most general level 1 state. Okay? So now we have to evaluate Q on the state. Let's call it psi, and we want Q on the state. Q on the state. Okay. So now let's see. There are two kinds of states that in doing the calculation, there are two kinds of states that one could keep track of. There are states which have a C0 have an explicit factor of C0 and there are states that don't have this explicit factor of C0. Now, all contributions with an explicit C0 must end up cancelling each other once we impose the physical state condition, once we impose the physical energy condition. Can somebody tell me why? I'm saying that this answer that that if we impose L0 on the state is equal to 0, which of course will follow from Q invariance, as we can see, but the entire contribution of C0, all states corresponding to C0, will just vanish once we impose L0 on state equal to 0. This is something we saw last class. Can somebody remind me? Okay, so remember the state that has an explicit factor of C0 in it is not annihilated by B0. Yes. Okay, but you remember that we saw that the set of states which obeyed L0 equals 0, L0 minus 1, then normalized L0 equals 1, and obeyed B0 equals 0 were closed on the Q. Remember how we argued that? Argument was that L0 with Q was equal to 0, but L0 with B was Q with B, B with Q. Now I might get the sign wrong. Sorry, I don't remember which way it was, but it was equal to L0. We saw that from the QBOB, remember? This is the whole L0. This is L0 matter plus constant. Okay? Therefore, the whole problem of Q cohomology can be done sector by sector. You can consistently restrict to states that are annihilated by L0 by plus G and B0. In particular, if you act on a state which is annihilated by B0 with Q, if that state obeys L0 equals 0, the remaining, the state that you get must also be annihilated by B0. Okay? So given aside, if B0 on psi equals 0 and C0 on and L0 on psi equals 0, then B0 on Q psi must be equal to 0. Okay? So, if in this calculation we get any contribution proportional to C0, that contribution proportional to C0 must be multiplying a factor of L0. So the only role of things proportional to C0 will be to impose the L0 equals 0 constraint. Okay? I'm saying this because, first just do it by calculation. I'm saying this because it saves us calculation. The states proportional to C0 are a little tricky to do. I mean, they're not tricky, they're a little bit of a pain to keep track of. The other states are totally straightforward. Okay? So in computing Q1 size equal to whatever, I'm going to ignore all states that we get proportional to C0. Just knowing that the thing proportional to C0 must be proportional to L0. L0 matter plus L0 constant. Okay? Now keeping this in mind, let's do the calculation. Okay, so let's add Q on this thing. So what terms in Q are important? Well, we have the C times T. So we will have terms like C minus 1 L1. And if we were keeping track of states with C0, we would also have terms like C0 L0. But we're not keeping track of the states, so just forget it. You already see that L0 appeared and C0. This is matter apart from the course part that we get the course computer. Okay, so please just forget about that. Okay, so this is the only thing. This is the only thing that will be of interest to us in the part of Q that comes from here. What about the part of Q that comes from here? Again, since we're not interested in C0, we have great simplification. Okay? Because levels must add up to 0. We should never get more than 1. Okay, the levels must add up to 0. Should never get more than 1. So what do we get? Either one of the C's is a 0 or one of the B's is a 0. Because the levels must be 0, 1, minus 1. Okay? But B0 annihilates the state. We're not keeping track of states that are C0. So none of those terms are. Is this clear? So the only thing we have to worry about is this. This is the only part of the operator Q that will be of interest to us. Apart from getting L0 equals 0 condition, which we know is going to come out. So we've already argued that last time. Is this clear? Okay? So what's the conclusion? The conclusion is that when we have Q on this, we only have to worry about this. Now what do we get when we worry about that? So firstly, I'm sorry. There's also here I forgot, of course, there's in the matter part there's the C1 L minus 1. This is also important, right? We have to keep all things where nothing is more than 1.
Because it's going
with the C minus 1. Okay? So now let's go. Suppose we had this on this. This term gives 0, but this term gives something non-zero. It gives us. This C1 acts with the B minus 1. Okay. So on this we just get 0. Okay. So alpha disappears from the state. With this B, we get some state that's proportional to. I'm not keeping track of signing the factors of 2. This won't matter at all. Okay. We get a state proportional to B times L minus 1 on P. Okay? And we will get a state when this L1 hits this alpha minus 1. Okay? Now what is L1? L1, the only term in L1 that's of importance, as we saw previous time, is alpha 0, alpha 1. Okay, so the alpha 1 will be killed. The alpha 0 will contract with A mu, but alpha 0 is P. Okay, so there will be some number times this plus some other number times P dot alpha into C minus 1. And if you work it out carefully, including also the C0 terms, if you work it out carefully, including also the C0 terms, you would get some contribution which has C0 and then something else with the physical state condition. Something else, some factor basically. Okay? Now, so this is the action of Q on states at level 1. Now we want that the state be physical, that be annihilated. Okay? Therefore we first demand that L0 is on state 0. That's Marshall condition. Fine. In our general discussion last time we said we would only deal with states that obey the Marshall condition. So let's omit that from us. Okay, so there's a Marshall condition. But there is also now the fact that beta must be 0. You see, these states can't cancel each other. This has C minus 1 and this has an L minus 1, which is matter, L matter. It is totally different. So beta must be 0 and beta alpha must be 0. Okay? So, physical condition. So alpha dot P equals 0 is exactly what I saw before. But in addition we have this beta is equal to 0.
Same state of the
It's the same. In fact that's where it came from, right? C minus 1, sorry. C minus 1 was multiplying L1, and L1 acted on that state. Right. So that's the sense in which, you remember, on those other states, Ci's can just be thought of as parameters on the first set of states. So since the coefficient of every Cn must vanish, that's where we got Ln vanishing. So this must be a subset of the decision set, as we see. Okay? Fine. So this is what we did. However, at this point we've taken our 28 oscillators and cut it down to 26. Okay? So we must also have some null states. So now let's compute which physical states are null. Okay? So are there any physical states? So states of this form, well, we can do better. We can work with BRST cohomology. Right? So are there any physical states which are Q exact? Well, we've already done the calculations. Tell me which physical states are Q exact? So what condition on alpha? What?
Equal to P, proportional to P.
Say again?
Proportional to P.
Alpha proportional to?
No, sorry.
So the states which are obtained by acting with Q. So these two are.
Okay, let me write one more step. L minus 1 matter of P is equal to alpha minus 1 alpha 0 at P. Okay? Hi. Which is P dot alpha minus 1 P mu alpha minus 1 mu or minus 1 mu acting on P. Okay, so now tell me what you said was completely right. So just let's say it again. What are they? So there's a two-dimensional vector space of Q exact states. Tell me, describe this two-dimensional vector space.
There is one gauge transformation
Which is this one?
which is this one.
Which means in terms of A, beta, and alpha, what is that? So what part was that?
Beta is 0.
Alpha equals 0, beta equals 0, and A mu is proportional to B mu. That's one of the vectors in this space. Okay, what's the second vector in this space? This one, right? And what is that in terms of the stuff?
So alpha is
A and beta is 0.
alpha is P dot.
I confuse you by sometimes writing alpha for A.
Yeah,
that's A.
So yeah, alpha is P dot A and B up.
Now, but what is P dot E? What does that mean? You see, but by you can get any value of any real number by dotting an arbitrary A with an arbitrary P, with any given P. So alpha equals anything. It's pure gauge. It's Q exact. Okay? So any value of alpha and any n mu proportional to p mu, any linear combination of these two, is Q exact. Okay? So Q exact states are alpha c minus 1 plus p mu alpha minus 1 mu on the side on preview. For any alpha and we could put a beta any multiples. Okay, so the Q exact states are these. Now Q exact state should be orthogonal to every physical state. Can you the only orthogonalities between level 1 and level 1? Can somebody argue for me that these states are indeed orthogonal to every physical state?
So C minus 1 will become 0 with.
Yeah, so this is Q exact and the physical state was equal to, let's call it alpha tilde C minus 1 plus, let's call it B mu alpha minus 1 mu on P mu, where alpha dot P is equal. Okay, so now that it's obvious that is what you say.
There is no V1.
There is no V1.
One will be 0.
Exactly. So because that's the absence of V1 for every physical state, this guy has nothing to contract with, so 0. And similarly here, the only thing, this one contracts with this, but it gives a P dot B in the contraction. And P dot B dot P is equal to 0 at the physical state. Okay? So, states that are Q exact are formable to every physical state. So we could have equally well determined the states that this set of Q exact states by just computing the matrix of inner products on the steady 6-dimensional state space. We would have found 2 null states. Everything else looks like. Okay, so in the end we got the same answer as before, because although physical states are a C-1, you see C-1 is pure range. So you can by BRST cohomology set to 0, and then physical states have transverse to momentum, but moving the amplitude by a factor proportional to momentum gives you 0. Okay? Fine. So that's all we want to say about this no-close theorem and cohomology and so on. And we'll now turn to a discussion of the scattering amplitude, now that we're armed with all this knowledge. But any questions or comments on this? Okay, even this exercise is worth doing at one higher level, seeing that you get the same answers if you do it. Okay. Okay, I now want to turn to discuss the scattering amplitude. This discussion is largely of, well, it's not very deep, but we should go through it just so that you know that scattering amplitude has all the consistency properties that you want. So first, let's remind ourselves of the formula of scattering. So we have scattering amplitude of various states and an integral over moduli. Okay, then had an integral for the position of all the unfixed vertex operators. For the I not belonging to fixed vertex operators. Okay, then you had a product of and let's put a factor square root G metric. So for each of these, integral to the right measure. Then it had a product over I belonging to the set of fixed vertex operators. Okay, and we had a factor of C and C tilde. C and C tilde for each of these operators at and then we had a factor of the vertex operator. Then we had a factor of the vertex operator for every kind of vertex operator. And then finally we had these factors of B del kg. These factors of B del kg for every modulus, and then we have the exponential of minus Sm plus Sm. Okay, this is the final formula for the scattering amplitude. It's been some time since we wrote this down before, so is every term here familiar to you? So is any term here that you can't remember what it means? Please tell me. We'll elaborate. del kg was the derivative of the metric with respect to the variation of moduli, of the kth modulus. Okay? So this k, okay, so good question. So I is equal to 1 to m, that's a number of moduli, and k, there's a product here, the product over k. And k is equal to 1. Okay? That round bracket meant the inner product, was the inner product of the space of that we defined, right? The diffeomorphically invariant inner product between between B, which has 2 indices down, and G, which has 2 indices down. So the inner product was B alpha beta, G alpha A, G beta B, del K G B, square root G in vector space. And you remember that if we chose a metric that was locally y equivalent to holomorphic metric, then B was traceless, which meant that its only non-zero components were BZZ and BZ bar Z bar. Also remember that B and C, but B was taken to have lower indices and C was taken to have upper indices, were y independent. Remember, I'll also remind you that the ghost was proportional to square root G, B alpha beta, square root G B alpha beta. Let's write it for B PC. Okay, where this operator P, if you remember, was half of was symmetrized derivatives minus trace. So P on C was del mu C mu minus plus del mu C mu minus G mu delta C. P is an operator that takes an object with one index to a traceless object with 2 indices. Okay? So you add the P on C, you get an object with 2 indices, it's traceless, and then you just take the inner product. Let me write this as P comma PC. But that bracket PC is the 2 index object, and you take the usual inner product in this form. Okay? And just to remind you again, in flat space, what does this, or any y in space? You remember how does this inner product go? Well, in that space, we got del Z bar C B was Z bar Z. Okay, let's work out. Sorry. So let's actually work out how this works when let's say we have flat space and we've got complex coordinates. So there's no square root G. So there's a BZZ. Then this has a GZ. Now the only component Z bar, GZZ bar, and then there is del Z bar, but that's a flat space, so it's just del Z bar of C Z bar sorry, just going to have this work. Yes, that's it. but we want to work the upper index. So see, this is some Z bar, right? So this was BZZ, del Z bar, CZ bar, which is the same thing as CZ, which is proportional to that. Okay, and it was this BZZ that we call it B, and CZ, which we call C. Okay, and we also checked when we worked all this out that when we took the variables to be like this actually was actually y this thing. You remember that if we took the metric to be e to the power 5 times del Z bar, you got the same answer for this denotation, the e to the power 5 series. Okay, very good. So, fine. So, okay, just every term of this on the blackboard clear. Okay, V is the number of conformal fitting vectors. It's the number of gauge invariances that are not yet fixed. M is the number of moduli. It's the number of directions extra directions that we have to integrate over the space of metrics that couldn't be reached from a particular choice of metric by conformal transformations, by Y transformations, Y integrals. Okay, questions, comments? Well, there was a single C from left movers and a single C from right movers. Right. There was. Let's see. So, if now you want me to. Basically, you see, there were two diffeomorphisms we had to. There were two additional diffeomorphisms we had to fix. Right? And remember where the C insertions came from. They were Faddeev-Popov hosts for gauge fixing, putting operators at particular points. Now we're putting operators at points in a two-dimensional manifold. Okay? So there were two delta functions, two conditions from that. That's what gave rise to the two C's. There's one C for every component. Okay, good. Other questions, comments? Fine. So now what I want to do is to explore various properties of this formula. Okay. So in order to do that, I'm first going to tell you about. So let me keep the formula on the board. Here for now. Okay, so in order to do that, let me first tell you about another representation of the coarse part of this formula. Okay, so firstly, also now, what are V's? You see, now we have a much better understanding of what these V's are than we did when we went through this calculation last time. Okay, you remember where we got all this from? Where we got all this from was by scattering physical states. But there's one physical state for every element of BRST cohomology. Okay? In the simplified way of thinking of it, there's one physical state in the C ghost vacuum, and corresponding to every primary matter operator, that is not itself a descendant of something. Okay? So the V's here should be thought of as primary matter operators that were not descendants of something else. Okay, if the V's were descendants of something else, that would be fine. It wouldn't change anything, as we will soon see. So more precisely, V is any primary matter operator, but two different operators that differ by a descendant, you will give you the same matter. So it doesn't matter which representative. Okay? Now, let's before we go on to study this formula in more detail, let's look at certain aspects of it. You see, what's going on here, we did this in some generality, but now let's look at the answer. What's going on here is that those operators that were fixed to points, also have a factor of C from the left and C tilde from the right multiplying the vertex. Now, you see, that's sort of satisfying. This factor of C and C tilde are satisfying from another point of view. And that point of view is the following. If you remember, when we worked out the BC host system, we worked out the state operator. And one of the things that we found was that the operator dual to the vacuum of the theory was what? C. It was C on the left and C tilde on the right. So if we did it. So what we're doing here is precisely inserting the operators, so the fixed operators. We're precisely inserting the operators that are dual to the special states we considered in today's discussion at the end of the last class. Namely, the operators that are in the closed vacuum, the operators that are in the closed vacuum, and the operators that are in the closed vacuum and for an arbitrary matter state, that is matter prime. Okay? Our procedure has told us that we should do that for some of the operators. For the remaining operators, we don't need this factor of C. We don't need this factor of C, that they will be integrated over the worksheet. This may worry you. You may worry that this operator will now not be BRST invariant. Because we know that something of the form that is C times V, where V is a matter primary, is BRST invariant. Check that. Okay? There are these V's without the C's and so on. All these things are, this is the kind of thing that this lecture is going to be about. Clear up all these worries. Okay? So let's go systematically. The first question we're going to ask is, well, this formula involves an integral over moduli space. But nobody has told, there's no God-given measure. There's no God-given measure on moduli space. Or perhaps there is, but it hasn't entered our discussion. Okay? So with what measure are you going to integrate over moduli space? This looks like a serious question. What does this formula even mean? If you don't know what measure you're going to integrate over moduli space. The great thing about this formula, as we'll see, is that it's invariant under the change of coordinates on moduli space. Okay? So that's the first thing we're going to try to understand. Okay. So invariance under coordinate transformations on moduli space. In order to understand that, we're going to take the closed part of this path integral and process it in a way that is sort of nice, independently nice, but a byproduct will be this understanding of this integral. Okay, so the first thing that we do is ask the following question. Suppose we looked at this closed action. Okay? We looked at this closed action and we ask, well, is there a way of taking the B and C fields and expanding them in an eigenbasis of something? So what I want to do is the equivalent of a Fourier transformation. The equivalent of Fourier transformation for a free field theory on, say, flat space. What?
BNs and CNs are a Fourier expansion.
BNs and CNs are a Fourier expansion. That's exactly right. But you see, now we're trying to be completely general. We're doing this on an arbitrary manner formula. Okay, exactly. So what we're going to do is, you see, the BNs and CNs have a property that they had good transformation properties under the quadratic operator, under the operator that you get. Well, hang on for 5 minutes. See what we're going to do, and you'll see that it will reduce to that in flat space, but it's more general. Okay, so you see, this operator P is an operator that takes a 1-index object to a 2-index object. So this is an operator that maps one space to another. So it's not some sort of square matrix. It's not mapping one space to itself. However, we have an inner product defined in the space of object with indices. Okay? So let's consider the operator P dagger. P dagger is defined by the the usual requirement. Okay? And it's easy to find an explicit formula for beta. It just takes a derivative, an appropriately lower derivative, and contracts away one of the indices of B. Okay? So we define this conjugate operator beta. Now let us consider the operator P dagger P. The operator P dagger P maps objects with one index to objects with one index. Because P dagger was the object that mapped objects with two indices back to objects with one indices. So this is a nice square operator and can be diagonalized. Okay? So it makes sense to consider the eigenfunctions of this operator. Okay? So let's suppose that we have this operator has some eigenfunction, let's call it Cn, with eigenvalue combined.
This is just show the Laplace. So we are just looking at the Laplace.
It's del square in that space. Yes, exactly. But you see, we want to make this discussion as general as possible because we want to apply to all Riemann series. So I don't want to specialize to flat space in this.
This will be a Laplacian of that manifold.
It would be exactly what this is. You see, this is a Laplacian. Right? It would be essentially a Laplacian, but acting on vector fields. Because CS an index. So it's not a scalar. Yeah. Okay, good. So fine. So we've got this equation. So suppose Cn is equal to P dagger P is Cn is equal to gamma n Cn. Okay. Now I want to show that by and large. Okay. Similarly, the discussion that we had for P dagger P, we can have a discussion for P dagger. Okay? So let's let the n run over all eigenstates and all eigenvalues of the operator P dagger P and the operator P dagger. Okay, now I want to show that there is a one-to-one correspondence between eigenstates of the operator P dagger and eigenstates of the operator P dagger P, provided the eigenvalues of these operators are not equal to 0.
Okay, this P dagger is always acting on the vector space of two indices.
P dagger acts on the space of 2. Space of 1. So these are completely different operators. A square matrix on the space of 2 index objects. Essentially, the Laplacian. There is a square matrix in the space of 1. Okay? Now, suppose there is a solution to this equation.
But the P dagger is not the Laplacian acting on
P dagger, I think it essentially is.
but I thought the P dagger, one of the indices was contracted.
Yeah, you're right. So, but let's see, how will it go? It would be sort of, P dagger will be del mu of d mu
It will be del mu, grad mu.
Yeah, you're right. It's not, you're right. It's whatever you get by doing P dagger. Sorry, I will not stay with one. Yeah, wait, is the other one also like the last? Yeah, that and then
the other one we don't contract.
Right, we don't contract. And when we now act with this, we'll say it's something like del beta plus del alpha minus trace. Yeah, you're completely right. It's very, very different from the Laplacian in the sense that the indices, one index is contracted with here and the other index is free, rather than the indices being contracted together. So that's what P, subtracting by the trace, this is what P dagger is. It's this differential. Alright, thank you. Okay? But at the Okay. Now, so consider P dagger P on Cn is equal to gamma n Cn. Suppose there's an eigenfunction of P dagger P that obeys this equation. Now let's take this equation. Okay, I'm rubbing this out also. Let's take this equation and act on both sides with P. Okay. Because these operators are associated, we get P dagger on Pcn is equal to gamma n times Pcn. Okay? So provided that Pcn is not equal to 0, provided that Pcn is not equal to 0, every eigenfunction of P dagger P, every eigenfunction with non-zero eigenvalue of P dagger P leads to an eigenfunction of P dagger with the same eigenvalue. Is this clear? And of course the reverse is also true. Okay? So there's a one-to-one map between eigenfunctions with non-zero eigenvalues of P dagger and P dagger P. However, if P on Cn was equal to 0, suppose P on Cn was equal to 0, then this statement would be meaningless. Because this is just an eigenvalue equation which is obeyed by zero eigenvector, which doesn't mean anything. Okay? So there is no statement about correspondence between the zero eigenvalues of the operators P dagger and P dagger P. Okay? So if we look at the operator P dagger and the operator P dagger P, its spectrum of eigenvalues coincides when non-zero, but these two operators may have different numbers of zero eigenvalues.
This just says that it's a subset. Why?
But we can do the other way around. So, if there was an eigenvector of P dagger P, this has proved with gamma n not equal to 0, this has proved that there is a corresponding eigenvector of P dagger with the same value of gamma. But now this argument is completely symmetric. We can repeat it by starting with P dagger. We get the same thing. So we have a one-to-one map of eigenstates with non-zero eigenvalues of these two operators. Okay? In fact, let's be more specific. So let's say that we've got that the eigenvectors are C0 I and I is equal to 1 to V. These are the zero eigenvectors of this operator. And in addition, there are Cn, okay, with eigenvalues gamma n. And let us choose these Cn's to be normalized under the norm, this bracket norm that we've been talking about. The bracket norm is just contraction multiplied by square root G integrated. Okay? Then, let's see if we... So, these things are normalized eigenvectors with eigenvalue gamma n for the operator P dagger P. Let us see if we can now find a formula using this result. Oh, by the way, something I should have said is that because this operator is, this is an omission operator. Clearly, so you take the dagger of itself, you take back on itself. And also it's a positive operator. But anyway, the important point is that P on Cn is equal to 0 is equivalent to P dagger on P on Cn equals 0.
It's possible. Is it from sign?
Oh, it's positive. See, let's act P dagger on psi. I want to show that all eigenvalues are positive. Okay, yes. Yeah, so I just take inner product. Negative, positive, negative. Yeah. Okay, but what I want to say is that if the only way that P dagger P can be 0 is if P on psi equals 0. This is the usual argument, right? Because P dagger P on psi equals 0, so let's contract the psi and use the positivity of the inner product. Then this is the inner product of the state P psi itself, the only way this can be 0 is if P psi is equal to 0. So there's two ways. When I say P is the eigenvalue of the operator P dagger P vanishes, that's the same thing as saying P kills the operator. Okay, good. So these are the 0 modes of the operators P. Okay? And then these are the other eigenvalues, the non-zero eigenvalues of the operator P dagger P. Okay? Now, given any of these non-zero eigenvalue states, we use this construction. We have that P dagger P, P dagger on PCN, as we've seen is gamma n Cn, gamma n PCN. And if we want to deal with it, okay, so let's say that Bn is equal to some alpha n, some normalization that I don't know, times PCN. Let me determine this normalization. So let's compute the norm of Bn. Okay, so the norm of Bn is the norm of PCN PCN, which is the same as Cn P dagger P Cn. What? I'm going to choose alpha. What? You're saying you want this to be the same as this? This is a
because these are products in two different spaces.
Right. But if A is equal to the dagger of B, then B is the dagger of A. This for
Okay. Fine. Yeah.
This is the definition of dagger.
Yes.
Yeah. Okay. So this is equal to Cn gamma n Cn. We chose gamma Cn to be unit normalized. So if we choose alpha n to be 1 by gamma n, and if we choose alpha n to be 1 by gamma n, this Bn is also unit normalized. Okay. So Bn is a basis in space of this other guy, which is of PP dagger, which is unit normalized. And let's also write down the host action. Well, this is leading to a point, by the way. Okay, so let's also write down the host action. So the host action is BPC. Okay. Now we can take C and expand it as we need some nice variable gamma n Cn. What? There's already a gamma n. Yes, lambda n Cn sum of all n. This is the Fourier expansion. Okay? And we can take B and expand it. Is there a beta n somewhere? Sum over n, beta n Bn, which is equal to sum over beta n PCN. Okay. Which is equal to and I'll separate out the contribution from the 0 modes. Okay, lambda 0 I C 0 I. And once again here I'll separate out the contribution from the 0 modes. Beta 0 J P 0 J plus sum over the remaining guys are beta n PCN by gamma. Okay? Now let's see what the host action becomes. Let's plug this expansion of C and B into this action. What do we see about the 0 modes? Firstly, what happens to these guys? What?
They're annihilated.
They're annihilated, exactly. Okay? They're annihilated. Okay, just for, right. These guys are annihilated because P kills it. On the other hand, these guys are annihilated because you can write this as P dagger on P, and P dagger kills these guys. So the 0 modes don't enter this action at all. So the only contributions we get are from the see, we have done that. Because these are eigenvectors of a Commission operator. Yeah. So we substitute this in. So what we have is sum over beta n PCN by gamma n, and then lambda MCM. Because our basis is orthonormal, this is the same thing as lambda M PCM. Thank you. So this is the same thing as beta n lambda n lambda n by gamma n PCN. Which is equal to because wait, there was an extra factor of it was being necessary.
You can bring the P.
Yeah, this P was this P. Thank you. Yes. So now we take it. Okay.
And we'll get a lambda.
Yeah.
Gamma n, which will cancel.
Yeah, but I have this is weird. I missed it. Because the final answer should have a should be a gamma. So sorry, so I messed up somewhere. So let me see where. Let me see where. I think it's the square root. Yeah, there's a square root, right? Yeah, sorry. So, okay, so let me do better. Since this is a positive matrix, I'll define this with a square. Okay, then this continues to be accurate. Our normalization continues to be accurate. Our 1 by gamma n continues to be accurate here. But when we do this stuff, we get gamma n squared. Okay, so this is equal to gamma n beta n lambda n. Okay, this is now an I formula. You see in particular that when lambda n is equal to 0, if lambda n is 0, that's the action. Having gamma n is 0. Okay, so in terms of the coefficients of this orthonormal basis, okay, this BC system has of course reduced to something very nice. Okay, you just have coupling between beta and lambda n. Okay, and there is this factor of the eigenvalue behind it. So the BC action is something very nice. But the key point that I want to make in all of this is that the zero modes do not appear in this action. Now, why is that important? That's important because we're doing a path integral dc dt. Now, what does it mean to do a path integral over a field? One way to give meaning to the measure of path integral over a field is to take that field, expand it in an orthonormal basis, and do the integral over the coefficients of this expansion. This everyone's going to tell, right? It's like doing the expansion, the path integral in momentum space for an ordinary field. Okay? So this thing means, now that we've sort of done things carefully, what does this mean? This means d product over n, d, have I called it lambda n? Okay? Product over n d beta n. Oh, this is derivation. Okay, do you understand? These are the coefficients of the expansion. These were the functions. These were the coefficients of the expansion. But I also have the products over the zero ones. Product I is equal to 1 to V and product J is equal to 1 to M. D, what did I call that? Lambda 0 of I. And D, I call that beta 0 G. This is what the path integral over the course means. Okay? And this part of the path integral is no trouble at all. It has this nice Gaussian action with which to play. However, the part of the path integral over the zero nodes, that is problematic. It's problematic because the action that we're doing the path integral over is independent of the zero nodes. Okay? Now, why is that a problem? That's a problem because, as you know, Grassmann integrals, the Grassmann integral of a constant is zero. If you do an integral over a particular Grassmann with a particular Grassmannian coordinate over a function that is independent of that coordinate, you get zero. Because the Grassmannian integral says the Grassmannian derivative. Okay? So, it looks now like we're in danger of getting zero by doing the path integral that we set out to do in order to compute string scattering amplitudes, because we've got these integrals over all the zero nodes. So what gives? The thing that gives is that in addition to doing the integral over the e to the power minus action, we also have all the insertions. Now, how many insertions do we have? Remember, the number of insertions of C were the number of unfixed gauge invariances. Unfixed gauge invariances were those gauge invariances that left the metric unchanged up to Weiland conformal transformations and highlighted the metric. But the action of a diffeomorphism on the change in the metric of a diffeomorphism is essentially given by the P operator acting on this diffeomorphism vector field. So the number of C insertions, which is the number of unfixed gauge invariances, is the same as the number of zero modes of the operator P. On the other hand, the number of moduli is the number of variations of the metric that is orthogonal to every gauge transformation. It's the kind of change in metric that you cannot achieve by one of these gauge transformations. Okay? So it's a metric variation such that it's orthogonal, metric variation, inner product, change in the metric due to a gauge transformation is zero. So metric variation, inner product, P with any C is equal to zero, which means P diagonal and metric transformation is zero. Okay? So what I'm saying is that what are the moduli? The moduli were those changes in the metric which could not be met by performing a gauge transformation, a diffeomorphism plus Y transformation on a standard metric. Okay? So it's the set, now that we have an inner product, okay, you can think of it as that set of metric variations that is orthogonal to every variation of the metric that you can achieve by a gauge transformation. But variations of the metric that you can achieve by a gauge transformation are simply P on V for any vector field V. This is how our metric changed. Okay? Therefore, if delta G is going to be orthogonal to P and V for every V, so this is 0 for all V, this means P diagonal delta G 0 for all V, which means P diagonal delta G is 0.
The vector mode for the metric change to zero. It's exactly this. It's those changes in the metric that have no overlap with changes that you can achieve by gauge transformation. Yeah. So basically, you're saying that any change in moduli should be a change in the tensor mode, because vector modes and scalar modes are not visible, because it should be achieved by some graviton. Some physical gravity. Now the P diagonal delta G is basically a vector.
P diagonal delta G is a vector. That is correct.
Okay, and you're saying that for the vector mode changes.
What do you mean by vector mode?
Because p delta D is a vector.
Yes.
Okay, so what you're saying is that that change in the metric is not a change. Okay.
P dagger delta G is
it's not a change in the physical degree of freedom. The physical degrees of freedom are actually the tensor mode, the graviton.
This kind of way of thinking, I'm not sure exactly what you mean by tensor mode. This kind of way of thinking will lead you to say that there is an infinite number of solutions to this thing. To P dagger D delta G is equal to 0. If I understand you correctly by what you mean by. Oh, sorry, just tell me what you mean by vector mode tensor mode.
Oh, yeah.
There is a small finite number of solutions to these equations. These are
this is a model.
yes.
Okay. There are only.
For instance, there are no solutions to this on the sphere. So this is not some very general decomposition into something. Okay? Just again, what is this? This represents a set of all metric variations that you cannot reach. Suppose you've got a particular metric, let's say some standard metric on your space. You look at all neighboring metrics on that space. And you ask, which of these are orthogonal to all changes in the metric that are brought about by Weyl and diffeomorphism transformations of your standard metric? That's what the zero modes of P dagger give you the answer to that question. But that's the question of what are the moduli. Those metric variations have no overlap with metric variations that you get by performing symmetric diffeomorphism and Weyl transformations on your standard metric. Yeah, that's why you need to integrate over the moduli. Because you should be summing over all metrics, most of which are Weyl or diffeomorphism invariant to, related to your standard metric, but not all. That's why you need to do the integral of the moduli. And that's how the moduli work. Okay? So, the zero modes of P are in one-to-one correspondence with the number of unfixed gauge invariances. The zero modes of P dagger are in one-to-one correspondence with the number of moduli. And now look, in our formula here, after promising not to clean this out, I cleaned it out. But in the formula for scattering amplitude, we had exactly as many C insertions as there were unfixed gauge invariances, and exactly as many B insertions as there were moduli. Is this clear? You remember we had, for every modulus we had B, del kg. For every unfixed gauge invariance we had a C times B. So that's what makes it all work. You see, the integrals over the zero modes of the B and C fields